let's look at 86. The base of a solid is the region in the first quadrant by the y-axis. Okay, y-axis. The graph y equals arctangent of x, that's this curve here, and the horizontal line y equals 3, and the vertical line x equals 1. So we have an enclosed region indicated by all the graphs provided in the problem. For this solid, each cross-section perpendicular to the x-axis. So let's think about what that direction is. X-axis is horizontal, perpendicular is going to be vertical. So we have a vertical base length is a square. Okay. What is the volume of that solid? This is a cross-section problem from 7.2. Vertical base length, we can connect the distance between the two boundaries here. The length of that base is going to be top minus bottom, so 3 minus arctangent of x. That's the base length. And now we're going to be building squares on top of this base. Okay. And the area of a square is base squared. So I just have to put my base expression into my area formula for this particular area, which is a square that we want to build. So my area is going to be 3 minus arctangent of x quantity squared. That's my area. Now that's only a two-dimensional calculation. If I want to move that to a third-dimensional value, I'm going to include integral on one side and dx on the other. That gives it that third dimension. And we have to also find the bounds. So the bounds are going to be in terms of x. So we look at the furthest left to the furthest right. The furthest left is 0. The furthest right is 1. So integral from 0 to 1. Use the calculator to evaluate the volume, 6.612 cubic units. 87. Our function f has a first derivative given by f prime. What is the x-coordinate of the inflection point? So let's look at what the graph looks like. We can put this in the calculator, in the graphing calculator, to see what this graph shows us. This is what the graph looks like. And inflection point off the derivative graph are the peaks and valleys. So there is a peak of the graph, there is a relative max. So that relative max represents the point of inflection of the original function. So we can use the second trace feature to find the relative max, and relative max occurs at x equals 0.473. Okay, number 88. On the closed interval from 2 to 4, which of the following could be a graph with a property of 1 over 4 minus 2, integral from 2 to 4 of f of t equals 1. So we want to do a little bit of work before we can match these graphs properly. So we want to know when this is going to be true, but I'm going to try to put that coefficient in an easier location to interpret. So 1 over 4 minus 2 is the same thing as 1/2, right? 1 over 2. And let's move this 1/2 to the other side of the equation. So if I multiply both sides by 2, I get 2 times 1/2 will go away to be 1. 2 times 1 is 2. So this is a little bit easier to interpret. I want to figure out which of these graphs shows a depth integral from 2 to 4 being equal to positive 2. Okay. So the first graph here, maybe it's tough to know exactly what the area of this is, but let's use a rectangle to help us out. I can draw a rectangle that has an area of 4, and we know that this region is taking up more than half of the rectangle. So we know that this area must be greater than 2 but less than 4. Okay, greater than 2 but less than 4. All right, because we know the area of this rectangle is 4. 2 times 2. Or sorry, this is a square. And then here we can also see a square of 4, area 4. But now if you look at this region here, between the curve and the x-axis, this is obviously less than half, less than 2. Probably more like a third. So we know that this region is less than 2. So neither of these are going to be correct because this is greater than 2, that's less than 2. We're looking for an area that's exactly 2. So now we have a V-shaped graph. I'm going to drop vertical lines at the endpoints, and both of these are triangles here. If if I do 1/2 base times height, 1/2 1 times 2, that's an area of 1. That's another area of 1. 1 plus 1 is 2. So this is our answer, our correct choice here. For D, just to kind of go through the rest of these options here, there's just this line showing, but if I just drop a vertical line at the ends, we see a triangle on top of a rectangle. This rectangle has an area of 2. This triangle has an area of 2 as well. 2 plus 2 is 4. That's obviously not correct. And then for E, this is a square with the area of 4, and that's not correct either. We're looking for area of 2. Okay, so answer choice C. Okay, we have a differentiable function, f of 2 equals 3, f prime of 2 equals -5. G of x is defined by x times f of x. Which of the following is a tangent line equation? So to find tangent line equation, we're going to find g prime. From g prime, we're going to use product rule to find g prime. Then we're going to evaluate the slope of the g graph by plugging in 2 into g prime. Once we have our ordered pair and our slope, then we can do point slope. But first, let's find the derivative. To find the derivative, x and f of x are two separate expressions that are multiplied together, so we got to go through product rule. F prime times g plus f g prime. X's derivative is 1. We keep the g function, we keep the f, and then g prime is f becomes f prime. So we have an expression that represents the derivative of g. Now let's clean it up and plug 2 in for all the x's. So we get f of 2 plus 2 times f prime of 2. F of 2, in the problem, they tell us f of 2 equals 3. And they also tell us f prime of 2 equals -5. So we can say 3 plus 2 times -5. 3 minus 10 is -7. That's my slope. Now to find my ordered pair, I'm going to plug in 2 in for all the x's for my original g function. So 2 times f of 2, I put that down here. So 2 times f of 2 is equal to 3. 2 times 3 is 6, so that's my ordered pair. Ordered pair is 2, 6. My ordered pair is 2, 6. We find the slope to be -7, and we put in a point slope form. Y minus y1 equals x m times x minus x1, and that matches answer choice D. Okay, for number 90, we have a closed interval from 2 to 5. Our function is told to be positive slope, positive first derivative, and a negative second derivative, which means concave down. So the graph looks something like this, potentially. Which of the following could be a table of values for f? So we know our graph will have positive slope, and it's going to display concave down. So what that means is that as we move from point to point, our slope is going to remain positive, but it will become less positive. So slope is positive, but it will be decreasing. So here, I just did change in y over change in x for all these ordered pairs here. So for the first two ordered pair, that's a slope of 2. Second and third order pair gives me a slope of 3. Third and fourth order pair, 16 minus 12 over 5 minus 4. 4 over 1 is 4. So we see that the progression of slope is positive, but it's not decreasing, right? The steepness should be decreasing if it's going to follow the pattern of concave down and positive slope. So we know this option is out. Option B is the correct one because 4, 3, and 2, these are all displaying positive slopes, but the slope is becoming less positive, so it's becoming less steep, right? A positive slope of 4 turns into the slope of 3, then turns to the slope of 2. This makes the most sense. C is incorrect because we're getting a slope of -4, -3, -2. These are all negative slopes, which contradicts what we know to be true and the fact that this graph is always going to exhibit positive slope. Okay, so answer choice B is the correct one. Okay, number 91. A particle moves along the x-axis given by acceleration, natural log of 1 plus 2 to the t. If the velocity of the particle at time is 2 at time t equals 1, then the velocity of the particle at time t equals 2 is we have this this formula that we've been using: position, our final position equals initial position plus displacement. Now we can also adapt this for one derivative down. So we can say the final velocity is equal to the initial velocity plus the displacement of velocity, or the depth integral of acceleration. Okay, we're just basically moving all these notations one derivative down. So using this formula here, we can say if I want to look for velocity of 2, I can start at velocity at 1 because that's what's given to me, and then I can bridge the gap between 1 and 2 under the acceleration function. So velocity of 1 is 2. I can use the calculator to find the depth integral of our natural log 1 plus 2 to the t between 1 and 2, and that gives me 1.346. Starting velocity plus the accumulation of velocity of acceleration, which is velocity. So if I add those together, we get our final velocity of 3.346. Okay, last problem here. We have function g provided by the definite integral from 0 to x of sine of t squared. Which of the following indicates where g is decreasing? So let's interpret what this is telling us. The depth integral of sine of t squared is equal to g of x. What that means is that the sine of t squared is sitting at the derivative level of g. Because if I force this sine of t squared through a depth integral, it's going to move this expression up to the g of x level. So that means the sine of t squared must be sitting at the g prime level if the depth integral will make it equal on par with g of x. So we can just say g prime is the sine of x squared. There's just a fancy way, a complex way of saying that sine of t squared is the g prime graph. So now that we know sine of x squared is g prime, let's go ahead and graph g prime. So we use our calculator, and if we see the graph is going to give us this shape. We can find the x-intercepts by using second trace 0. And let's also interpret what's going on here. Whatever is in the positive region of g prime indicates where our g of x is going to exhibit positive slope. Anything below is going to indicate where g of x is going to exhibit negative slope. Anything on the x-axis represents where the slope is 0. So wherever, so we know that this g of x is going to be decreasing wherever it's below the x-axis. So just between 1.772 and 2.507 is where our graph of g is going to be decreasing because it'll exhibit negative slope.